Hello everyone, welcome back to college algebra course. Today in this video clip I'm gonna cover two sections, 5.2 and 5.3. In 5.2 I'm gonna show you how to roughly sketch a graph of a polynomial function given just information that we have from the polynomial that they gave us. And then on 5.3 I'm going to talk about the rational functions. It's a type of function that's constructed from polynomials. Okay, so let's start with 5.2. It's out of ink already. 5.2 graphs of polynomial functions. I actually mentioned this, and I showed you a couple of graphs in the previous section 5.1. But let me just give you more examples in here, show you how we roughly sketch a graph from a given polynomial function. Okay, so let's start with the example. Example: say you have a polynomial f of x equal to 2 times, say x minus 1. I would say x minus 1. X minus 1 square times x plus 2 times x plus 1 cubed. And I gotta say this, in the book they show you how to factor this out to figure out the polynomial, but I claim that would not be a good idea. That's actually a bad idea. You should start working straight from this type of polynomial. After see the factor out, I factor everything out for you already. I show you the polynomial in the factored form. You should keep it this way, and we're gonna get information from here without multiplying everything out. Okay, without multiplying everything out, without factoring everything out, that would not be a good idea. Okay, so what do we get from here? First of all, the leading coefficient. Coefficients. It's the number right here. See all linear factors? This is actually 6 factor total. Leading coefficient is 2. It is a positive number. You have a positive leading coefficient. According to what we learned in the previous section, whenever you have a positive coefficient, the graph tends to go up. Now let's talk about the degree. And I claim that this polynomial degree is 6. How do I know it's 6? Well, you have 6 linear factors in here total, or you just add the multiplicity together. 2, 1, 3, right? It's 6. You write this way if you want. 2 times x minus 1 times x minus 1 squared, right? And then x plus 2, and then what? I'm out of room, so let me write it down here. Times x plus 1 times x plus 1, and then times x plus 1. You got 6 linear factors total. Add up, degree 6. Multiplicity, 2 plus 1 plus 3, 6. That's the degree. So positive leading coefficient, even degree, according to what we learned before, the shape of the graph tends to be this way. Okay? So, as I said, we just try to sketch a graph. We don't know the exact graph yet. And in order to know more about this graph, you're going to take calc 1, okay? Calc plus 1, and we learn about the derivative, and you know more about the local max and local mean. But for now, at least this is how much we can get from just a polynomial itself. Alright, so degree 6, you know that this graph has at most 5 turning points. So maximum 5 number of local max and local mean. Okay? Could be 3, could be 1, but at most 5 turning points. Alright? And now, what about the intercept? Intercept, we talk about the x-intercept now. You have 3 x-intercept. 1, -2, and -1, right? And remember, we talk about 3 things at the same time: the x-intercept, the linear factors, and the zeros. Okay? We have zeros. Here's x equal to 1. Right here, so I have more room. X equal to 1, x equal to -2, and x equal to -1. 0 is the value of x, so when you plug into the function, it makes the function equal to 0. So when you plug in x equal to 1, you got what? 1 minus 1 equal to 0. 0 times whatever is still 0. Okay, so x equal to 1 with multiplicity 2. because you actually have two zeros of x equal to 1. Here. X equal to 1 and plug them here. Another x equal to 1 right here. And then similarly, x equal to -2 is another 0 of the polynomial. You plug in x equal to -2, -2 plus 2 is 0. And then make the whole function equal to 0. But this is multiplicity 1. And then the last one, x equal to -1, is another 0 with multiplicity 3. So you have 6 zeros total. And that's also matched up with the degree. 6 zeros. Polynomial of degree 6. And with those zeros, you have the linear factors. What are they? X minus 1 is a linear factor. X plus 2 is another linear factors. And then x plus 1 is a linear factor. This is multiplicity 2, this is multiplicity 1, and this is multiplicity 3. It's match up. And then you have 3x intercept. X equal to 1, intercept is 1, 0. X equal to -2, intercept is -2, 0. And then x equal to -1, you got what? -1, 0. So in this section, we are focusing on the graph. That's why I put the intersection first. You have 3 intercept. Okay? And then depends on the multiplicity, as we mentioned last time, we can determine what type of intercept. Either it crossing the x-axis or it's touching the x-axis and bounce back. So 1, 0 right here, multiplicity 2, even. Even multiplicity, the intersection is kind of touching. Okay? The form of which is tangent, touch. And for the second and the third intersections is odd multiplicity, 1 and 3, they're odd numbers. And those two intersections are going to be crossing. Okay, so touching. Those two, this is crossing. Okay? That is how much information I know from this polynomial without any graphing calculators or graphing tools that we have. Alright, but nowadays we do have graphing calculators, so let me just sketch a graph in the graphing calculator, and it shows this matchup with what we have in here. And I already graphed this. Graph looks like this. It should be like this. Leading coefficient 2, degree 6, so the graph tends to be like this. With 3 intersection, right? Intercept at 1, 0 right here. -2, 0 right here. -1, 0 right here. Okay? So it should be like this. Let me use a different color because the space is small. So. -3 right here, -2 right here, and then 1 right here, 0 right here. You have 3 intercept at 1, 0, -2, 0. Oops, I wrote it wrong. This is -1, and this is -2. That's what I meant. Okay? -1 is right here with this intercept, and -2, 0 is right here. The cross in the x-axis. And you see that we have the y-intercept right here. Question, how do we find the y-intercept from here? Well, it's in general case for any kind of function. Whenever you want to find a y-intercept, all you have to do is plug in x equals 0 to find a y-intercept, right? Plug in x equals 0, right? So f of 0 is equal to 2 times 0 here, so -1 squared, -1 squared. 0 here, so you got 2. And then 0 here, 0 plus 1 is 1, raised to the 3rd power. So this is 2 times 1 times 2 is equal to 4. So this point right here is at 4. The y-intercept is at 0, 4. That's all you know. Okay? And in this type of problem, you should expect to have what? This is a local minimum. This is a local maximum somewhere in here. It's not at 4, okay? It's somewhere in here. And then this is another local minimum. That's just a type of graph that you have. And you can apply this type of example to other exercises in your homework and the test pretty much the same way, just different degree, different numbers. Okay? Now, let me move on to the next section of 5.3. I'm going to talk about another type of function. that is constructed from polynomial. Okay. This is called the rational function. 5.3. Rational functions. Okay. So first of all, I'll give you a definition. What is a rational function? The rational function is a function defined this way. You have a function that's constructed by having a polynomial divided by another polynomial that we're going to call a rational function. So a rational function is a function of the form polynomial over polynomial, rational, okay, ratio. So for our convenience in this clip today, I'm going to call the numerator polynomial by p of x and denominator by q of x. Okay, where p of x, q of x are polynomials. All right. An example. Let me box this first, make it stand out, and then I'll give you an example. Okay, example. Say f of x is equal to x plus 3 over 2x squared minus 4x plus 1. This is a rational function where px, the numerator here, is a polynomial of degree 1. It's linear, okay? And the bottom, q of x right here, is a polynomial of degree 2. Okay? It's a fraction of polynomials. Okay? How about this? F of x equal to 3x squared minus 4x plus 7 over 2x plus 1. Now this is also a rational function. Top px is polynomial of degree 2, the bottom is degree 1. Okay, still rational function. Or even this. Say f of x is equal to 3 over 4x plus 1. It is also a rational function. Remember what we learned last time in 5.1? Top right here, 3. The constant itself is a polynomial of degree 0. And the bottom right here is obviously degree 1. It's still a rational function. So you can see it this. Say f of x equal to 4 over 5. It is still a rational function. Okay? Polynomial of degree 0 over polynomial of degree 0. How about this? F of x is equal to 3x squared plus 5x plus 1. You can see right away this is a polynomial, right? Degree 2, quadratic function. It is also a rational function, if you can think of it this way. Over 1. All right? So rational function is going to cover all the real numbers, all the polynomials. So this is a big thing. Okay. Now we're talking about something called proper and improper fraction. So recall in total numbers, 3 over 5 is a proper fraction because the numerator is smaller than the denominator. But if you got like 5 over 3, you call this one the improper, right? The number, this is proper fraction. This is improper fraction. Because this one right here, you can do a long division. This is 5 over 3 is equal to 1 plus 2 over 3. Okay? So improper fraction. And similar idea can carry over for rational functions, polynomial over polynomial. We also have proper and improper fraction. So this one right here is proper fraction in terms of the degree. This is what? Degree 1 out of degree 2, proper fraction. The second one right here is improper because it's degree 2 out of degree 1. Okay, and this is improper right here. This is proper. This one degree 0 over degree 0. I think it's improper. I'm sorry, it's improper because we can't do any long division with this. Okay, that is pretty much the definition. Now let me move on to the next item. I'm going to show you some just basic properties and some calculations on rational functions. Okay. And I'm going to sketch a graph of rational function as well. So I should say with rational function and the graph, just in case the book didn't mention. Okay. To some properties. First, let me talk about the domain of the rational function. Let me give you an example, an easy one. F of x is equal to 3 over, say, x plus 2. This is a fraction, okay? 3 polynomial degree 0 over x plus 2 polynomial degree 1. The domain of this thing is all real numbers except x equal to -2. You guys see why we don't by -2 as a part of the domain? Because when you have x equal to -2, -2 plus 2 here is make the denominator. It makes q of x equal to 0. And then you have 3 out of 0, it makes the fraction undefined. So everything except for -2. Well, when you guys do the homework, this is one way that you guys write your answer. What's domain or real number except, and then they give you a box, x equal to, and then you have to find it. Or you may see this in a set notation. All real number x, and x cannot be equal to -2. This is another way of writing the domain of the rational function. Or you can use the interval notation. Say what all numbers from -infinity all the way to -2, but parenthesis, excluded, not include -2. And then union from -2 to infinity. And this is another way of writing the domain. So one of those three ways, the ways that we use them to represent our domain in our work. Okay? That's about domain. Let me give you another example. How about this? F of x equal to 2x minus 1 over x squared minus 4x plus 3. Now, this new example, we have a polynomial of degree 1 out of polynomial of degree 2. And this is still a rational function. So how do we find the domain of this function? Factor the bottom out. Factor q of x out. This is 2x minus 1 over, if I factor this out, I'm going to have x minus 1 times x minus 3. Okay? So the domain is what? Let me just write one of the way. Let me write all ways. All real numbers x, all x, except x equal to 1, x equal to 3. Okay? Everything is good except for x equal to 1, x equal to 3. Or you can write this way. All x, x cannot be equal to 1, x cannot be equal to 3. Okay? Or if you want to use the interval notation, it's going to be this. -infinity to 1, union from 1 to 3, and then union from 3 to infinity. Either one of those three ways is going to be good ways to represent your domain. Okay? So, whenever we talk about domain, we are focusing on what? The denominator. Alright? So how do we find it? We are ruling out all the zeros of the denominator. Okay? Everything except for the zeros of the denominator. 0 means what? All the values of x that make the denominator equal to 0. As we learned before. Alright? So in general, the domain of a polynomial, of a rational function, is domain is all real numbers except zeros of the denominator. So I'm going to use q of x for denominator. Okay? All real numbers except for 0 of denominator. Okay? So how do you find a 0? You factor the denominator out. You can find a 0. And that's what we learned on 5.1 already. Okay? That will be the first thing that we learned about the rational function. Next, I'm going to talk about some properties of the rational function that you have not seen in the rational function, in the polynomial function. Something called the asymptote. Okay. So in general, the asymptote is a line for now. It's a straight line where the graph of the function getting closer and closer to the line and never intersect at infinity. Okay. It could intersect somewhere in the middle, but when the graph keeps extending to infinity, the graph will never intersect the asymptote, but just getting closer. Okay. And we're going to learn three types of asymptote today: the vertical asymptote, the horizontal asymptote, and the slant asymptote. Our book calls the oblique asymptote. Okay, so let's start with the asymptote, the vertical one. Number 2, vertical asymptote. Okay, and let me abbreviate it by VA, stand for vertical asymptote. So how do you find a vertical asymptote from a rational function? As usual, let me start with an example. F of x is equal to 3 over x plus 2 then. The same example that we had before. And you know that domain is all real number x. X cannot be equal to -2 already, right? And then I claim that the asymptote is x equal to -2. If you ask me why is that for now, well, I always say this. It's beyond the scope of our course for now. That is a very fancy word. I encourage you to take calculus 1 after this and pre-calc and then calc 1. Then we talk about limit and you know why. But for now, just by looking at the function, you can tell that the vertical asymptote is x equal to -2. Okay? It's kind of opposite with the domain. Domain is everything except for -2. Then the vertical asymptote is x equal to -2. And the graph is like this. Rational function and their graph. So I'm not separate them. Talk about them together. Okay. Let me use green color. This is the vertical line, -2 right here. This is the vertical line, x equal to -2. And the graph of this function is this. I'm going to use red color now. Okay, and this way. Okay. And this is my x-axis. This is my y-axis. The two red curves are the graph of the rational function 3 over x plus 2. You see what? The dotted green line right here is we call the vertical asymptote, and the graph is getting closer and closer to the green line. When x is getting closer to -2 from the right, the function is going up, right? Getting closer to the line, but never intersect. X approaching -2 from the left. Later on, count 1 and say limit x go to -2. Okay, and the graph is getting closer and closer to the vertical line as well, but never intersect. And of course, by similarity, you see that we're going to have another type of asymptote right here, which is called the horizontal asymptote. The graph is getting close to the x-axis when x goes to infinity, or x goes to -infinity as well. But now we're just focusing on the vertical asymptote. And when we get to the horizontal asymptote, I will show you how to find the vertical asymptote. Okay? So, for now, you see what? The way we find the vertical asymptote is kind of by looking at the domain and the opposite of it, right? It's all real numbers except for x equal to -2. We have a vertical line right here, x equal to -2. That's the vertical asymptote. Let me give you another example. F of x equal to, say, 2x plus 1 over x squared minus 4x plus 3. The same example that we had before. And then I'm going to factor this out. 2x plus 1 on top over x minus 1, x minus 3. Domain, as we learned before, D stands for domain, okay? All real number x, x not equal to 1, x not equal to 3. And guess what? In this rational function, you guys are going to see two vertical asymptotes. Vertical asymptotes, x equal to 1 and x equal to 3. Okay, and let me sketch a graph of this one for you. See? This is the x-axis. This is the y-axis. Alright, we have two vertical asymptotes. X equal to 1 right here. This is x equal to 1, another one right here. X equal to 3. Okay. I want to make sure it's right. Let me try to sketch a graph on my laptop and I'll show you the graph. So I'm going to graph this. Graph y equal to top point is 2x plus 1.